I want to show you some stuff that's not really part of this course, but I think it's interesting to look at. And I want to generalize things as much as possible. And I'll start by looking at derivatives. When you say the first derivative and the second derivative, that kind of makes sense to us, right? And at some point, we use some sort of notation for derivatives. So when we get to the first derivative, the second derivative, the third derivative, and when we get to the fourth derivative, we don't put 4 primes anymore. We change the notation to this 4. And when it gets higher, it gets higher. So in general, we use the notation with the superscript, with the exponent superscript, and we use a number in parentheses to denote that you're taking some sort of derivative or something. And this makes it convenient for us to write formulas like Taylor's polynomial out using derivatives. The thing about Taylor's polynomial is that it starts off with the 0th derivative. What do you think the 0th derivative is? The original function, right? So when we think of the 0th derivative, we can think about that as the original function. All right, I just wanted to bring this up because when we do integrals, we could take a look at a single, double, or triple integral, right? And in general, you can write that as just an integral, and depending on what it is on the bottom, whether it be a one-dimensional object, or a two-dimensional object, or a three-dimensional object, if we have this object that you're integrating over defined, then we know what type of integral it is. We know that it's a triple integral if your object is a solid. We know it's a double integral if your object is a surface. And we know it's a single integral if your object is a curve or an interval. So we can think about a 0th integral if your object is a point. That's a 0th dimensional object is a point. Okay? And that just means we're going to deal with the original function and evaluate it at the point. All right? So when you see these integrals, these theorems can be written, if you write it with a single integral, so the divergence theorem, for example, if you say that's just a single integral over, they use E, yeah, we've been using E. If your equation looks like this, you should know that the left-hand side of this equation is a solid, and you're taking a div of some vector field, and there's a dv there. So you know that this has to be a triple integral, even though you don't see 3 integrals there. Okay? In some textbooks, that's what they do. They don't expand it to double and triple integrals. They just write a single integral, and it's up to you to look at the object and decide whether it's a double or triple integral. Okay? All right, so where am I getting at? I'm getting at the fundamental theorem of calculus. So let omega be a function. And this, I'll try to be general. I'll be as general as possible. This is just a function. It could be a scalar function or it could be a vector field. And then d omega is a derivative. And then let M be a geometric object and in math they call this a manifold. It's a little taste of topology. This is a topology term. It's a manifold. It's an object with a boundary, and more specifically a boundary and we'll let the notation with the partial be the boundary of M. Okay? So that means we can write this in simpler terms. The integral of a derivative of some function over a geometric object is now going to equal to the integral of the original function evaluated at its boundary. This is the fundamental theorem of calculus. And I've already convinced one student to get a tattoo of this, and she did. So if you want a tattoo, this is the fundamental theorem of calculus. I was going to get one on the side of my leg. Just the integral sign, though. You know, look at the integral sign. Isn't that like a beautiful symbol? It's like an S that's been extended, elongated. What? Math has a lot of cool symbols, but I think the integral is really a cool symbol. Yeah, so I was going to get one on the side of my leg, and I didn't. But if you want one, you should get one. Just take a picture and show me. Or if you get one of this. This is a cool tattoo. Other ones I've seen are the Mobius strip with the ants crawling around it. Somebody had that in the back of their neck. Another cool tattoo is e to the I pi is equal to -1. That's another really, really cool, powerful math equation. It's a simple equation, but look at the constants. It has e, it has I, it has pi, it has -1. And if you put -1 on the other side, which is what some people do, now it has 0, another important number in math. Anyways, just ideas for tattoos, in case you're interested. Christmas, you know, you can ask for a tattoo for Christmas. Anyways, oops. So, if we say this in words, it can apply to Green's theorem, Stokes, Gauss, fundamental theorem of line integrals, and it even comes back to the fundamental theorem of calculus. Except, you know, the idea of one less integral brings us down, if you have a single integral, one less integral is a zeroth integral, which in the previous page we kind of established as it's the original function being evaluated at the endpoints. Okay, so I think this is really the sentence, this is the equation that glues everything together, everything that we've been doing in chapter 16. And this carries on. I think Thomas asked earlier about like vector fields in 4 dimensions and stuff like that, in 3 and 4 dimensions, and using triple integrals. Those do exist in those other places. I've only seen them theoretically through this equation, but I haven't seen a working form of it. I don't know if it's something that's useful for physics or engineering. So I haven't seen anything that applies this idea in higher dimensions than what we've seen. But it's out there, it exists, and this is a way to denote it. All right, so that's fun. Now let's take a look at your exam. So it looks like your exam might have 7 questions. We're looking at a problem from the first exam being brought in here. Not an exact problem from the first exam, but ideas from the first exam. And so in the first exam, we talked about a lot of things. We talked about parametric equations, polar, conic sections, and stuff like that. But for that, for the final exam, I'm going to focus on parametric curves and motion. So there's, I don't want to just restrict it to a projectile problem, because there's other things that are involved with motion, like curvature and the Fernet frame and stuff like that. So any of those ideas, whatever I can compact into one problem. So it's like, you know, I'll have 1, maybe 2 equations or functions or curves or whatever it is, and then I'm going to ask you to work with that. The second one, I'm going to take something from the second exam, and initially I had something that was just focused on optimization, but I also wanted to test you on some gradients and directional derivatives, and then some optimization as well. That would include the second derivative test. I'm not going to include Lagrange multipliers there, so if you're looking to free up your brain with content that you don't need to study Lagrange multipliers for the final exam. Now the other questions will just focus on chapter 16 stuff. You have to know how to compute those integrals. Path, line, surface, and flux integrals are the 4 types of integrals that we learned. But we also, math is kind of cumulative. We also need to know how to compute double and triple integrals, which is from chapter 15. So that's important. You have to know what the gradient is. That was from chapter 14, to be able to do some of these things. And then some of the new derivatives of vector fields that we learned are the div and the curl, and that's all kind of embedded in the last 3-4 big theorems that we've had. So that's these are problems 3 through 7. We'll focus on chapter 16. So I dug some problems out from the book that you can focus on. The review, yeah. Oh, instead of 6? Yep. Change that right now. So I looked through the end of chapter 16, the review section, and I think the concepts are important. There's a bunch of true-false. I think that would be good exercise for you, but I'm not going to ask you any true-false questions, so you don't have to stress too much about that. But if you can just look through and try to answer them and check, I think they have the answers in the back of the book to see if you're able to answer them correctly. That would be good. But in terms of the actual exercise and problem solving, I found some information broken down by the types of theorems that we were focused on. So number 13 and 14 kind of focus on the fundamental theorem of line integrals. The next set focuses on Green's theorem, and then Stokes and Gauss. And then so problems that are similar to that would be good to study for the test. Yeah. Yeah, 1 page of notes. I also have the quizzes, the last 2 quizzes, the take-home quizzes that we have, and the solutions are up here in case you want to take a look at them. And I don't remember how many other worksheets we worked on in class. I think we worked on some worksheets in class, and then that kind of wrapped up and became a quiz online or something like that. But I was able to only find the solutions to last worksheet that we did, and that's available here as well. But we went over it in class already, so you can look at the notes in class, you can look at the video from that particular class, whatever day that was, or I actually have the solutions typed up. Okay? Yes? I guess so. I don't think you'll need it. Wait, let me think. Do you need it? Yeah, you just bring it just in case. I think the integrals are, I don't know if I just have you set it up or you actually compute it. So, yeah, maybe you should bring your calculators just in case you have to compute and find decimal value for an integral or something. I don't know. Any other questions? All right. Yes? No. I usually like those and some random questions. I do that for my stats class. I just ask random questions from the whole semester. And I usually do that for my calculus classes too. But try to fit this in 3 hours worth of test taking, so I decided to knock that out. Any other questions? Yeah. Wednesday at 2. Wednesday the 14th from 2 to 5. Technically, it starts at 2:10 and it ends at 4:40, but we'll just round it to 3 hours, 2 to 5. So I'll be here a little bit before 2, and I'll stay here till 5 o'clock. So this is on Canvas now. It's accessible. I think. I hope. There's sometimes I forget to make it public, but yeah, and it's right on top. So that's the first thing that you should see when you log into Canvas. All right. Well, we got a couple of options. One, we can try to do some problems from either the homework or from this set of questions that I showed you. Well, or we could be done and go. Nobody? If there's anything that you'd like explained or something like that, if it's like a specific problem from the homework, You can send me an email if I'm not too busy. I could try to make a quick video of it and then I'll post it online, something. Did I post stuff? I didn't post videos here. Oh, that's my other class. I have a whole bunch of videos for another class. So, what do you guys want to do? You want to work on a problem? All right, let's work on a problem. So here are the set of concept check problems from the back of the book. I just took a snapshot of it and put it in my notes. So I think trying to explain things in words would be good. If you can study with somebody else and then talk to them about it, the idea of being able to articulate this, I think, would be a good advantage for kind of like knowing what you're doing. So if you can explain what a conservative vector field is and what a potential function is, not just do it, but actually explain it in words, that would be good. What is a parametric surface? What are your grid curves? We didn't talk about grid curves, but you can certainly look it up in the book and you'll see. I think we did talk about it. Remember when we were graphing, I said the number of partitions, if we have, we're trying to parameterize a sphere, and then if we only do the 3 partitions for theta, then it's not going to look round. It's going to look like triangular or something like that. That's the grid curves. What is the area of the surface given the equation z is equal to g of xy? That's one of the last things we talked about yesterday was a ds, d capital S without the arrow on top. So that would be your answer to that. So if you can look at this and be able to relate to the things that we've been doing, to the integrals and why they're significant, that would be good. Here are the exercises. I think 13 or 14. Let's do one of those. So pick one. 14. So you guys didn't want to go, huh? I was so hoping you wanted to go. Anyways. Oops, what's going on? Show that f is a conservative. Show that f is conservative, and use this fact to evaluate this thing. So, in this case, they're kind of telling you f is conservative already, but you can go through the motion of showing it by taking the curl of it, because remember, the curl of a conservative vector field is 0. John?
Yeah, that's what I was going to ask.
Oh.
Like, here's a shortcut.
Yeah, so you can, I'll just put this on the side without doing it, show curl of f is equal to 0. Now, is this a 0 constant scalar or a 0 vector? So that's another, so those are little minute things that may or may not be important, but I think if you can look at these little nuances and know what they're about, like when you take the dot product of 2 vectors, you get a scalar. When you take the cross product of 2 vectors, you get a vector. So if you can get those kind of down in your memory, in your brain, then that would be good to remember. Once you know it's conservative, then you have an advantage for finding the line integral. So we have the curve C, which in this case is just a line segment. And the idea is that if f is conservative, then we should be able to find a gradient, or f is actually a gradient of some function, and that function happens to be called a potential function. And then really this is a matter of fundamental theorem of calculus, where the integral of a derivative of a function over an object is equal to one less integral down. So if you have a single integral, one integral down is just you're evaluating it, and that's you're evaluating the original function without the derivative on its endpoints. Or let me just put the boundary of C, which is the endpoints. So this is trying to exploit the big fundamental theorem of calculus idea. And then so the actual work is just you take your function, you put the endpoint here minus the function, and then you put the start point. And you have the starting and ending point. Now the fact that they say it's a line segment is not really going to matter as long as you start from here and end to there, then your answer is all going to be the same. Okay, so let's find the potential. We got our original f. Let's take e to the y, and this is in the first component. So this must have been This must have been obtained by taking the derivative of some potential function with respect to x. And so if we want to recover that, we need to take the antiderivative with respect to x. And then when we take the antiderivative, we have a plus c, the c with respect to the variable x. And so we have two other variables, y and z, that x thinks it's constant. So we have to make space for that if it exists there. And then we'll do the same thing, this is x e to the y plus e to the z. And then we would get an antiderivative with respect to the y, x e to the y, plus y e to the z, plus another constant with respect to y is going to be x and z variables. And then y e to the z is going to be y e to the z plus constant. Now, some people do it differently. I don't know if you've seen it. They take the antiderivative once, and then they take the integral, or no, they take the antiderivative, and then they take the derivative with respect to the other variable, and then take the antiderivative, and then take the derivative with respect to the other variable. I think that's a nice way of doing it. That's going to be safe, and you're not going to miss anything. This, you might miss something, so you just have to be careful and watch out. And the idea, I saw this when I was looking at the quiz, is that if you see something happen in two different places, you don't say there's two times that. You don't add this plus this. This happens here and this happens here, so this is just going to happen one time in our potential function. And then these are functions of x and y, which has nothing to do with z, so they would fall into this category as well. So your possible potential function in this case will definitely have an x e to the y. Okay? And then so if we try to capture the other components of this, we see an e or y e to the z here and y e to the z here, which is constant with respect to x. So this must have a y e to the z here also. That, when you took the derivative, would have disappeared with respect to x. And then that about covers it. We covered everything except for the constants, and the constants are kind of taking care of themselves. And so if you want to throw another constant in here, you can, but we're on our way to integrate, and when we integrate, those constants will go away anyways. Okay? So none of them are multiplied by 2. There's only one of each things that you see. Yeah?
Okay, so how did you determine that the constant was y?
I'm just saying this has the constant y e to the z in there because it's a function of y and z, and that would have disappeared. Just like this here also probably had a constant x e to the y. Yep. So it's always good to check potential. It's always good to check by just taking the gradient of this. Take the derivative with respect to x, derivative with respect to y, derivative with respect to z, and see if you're going to get back your original vector field. And if you do, then that's good. You did it right. And if you don't, you did it wrong, or maybe it wasn't conservative to begin with. So check your work. And then at this point, we invoke the fundamental theorem of line integrals by just figuring out the end is 403, the beginning is 020. So your line integral over this curve is equal to f of, what is it, 403 minus f of 020. And then you just put in those values. 4, 0. Oh, so well, yeah, when you put this in, you're going to get 0, and then the 2, right? Yeah. 2. So the 2. Okay. So that's the value of your line integral. Any questions? All right, let's do another one. Maybe a Green's theorem problem, 15, 16, 17. I guess we got those choices. What do we want? 17? So let's evaluate Green's theorem. Now Green's theorem is on the plane, so you should expect this to have just the x and y without a z. And Green's theorem, you might see Green's theorem written as that f dot dr business, or most of the time though you'll probably see it written like this. This is another differential form, but you can extract. You should be able to extract the vector field from here, right? So f is a vector field made of, and the p function and q function, those are the names that they use here. So f is actually equal to x squared y negative xy squared. And if this was conservative, since this is supposed to be a closed curve, C is a closed curve, then this is going to be 0. But we're not going to. It's not conservative, otherwise they wouldn't give this to you. The other important part when you're dealing with Green's theorem is to identify the curve. So you're integrating a line integral over a curve, the circle, with a counterclockwise direction. So identify your curve, because you're going to need to figure out what's inside of that curve. That's going to be your domain D. Okay? So according to Green, integral of p dx plus q dy over a curve is equal to the double integral. So this is just a regular double integral because it's flat on two-dimensional plane, not a surface. And then we have to identify what the domain D is. So it's going to be a double integral of dq dx minus dp dy. So you could just choose to memorize this formula or write it down, as Green's theorem. But it actually, that it does come from the curl. If you take the curl of this vector right here, I know it's in 2 dimensions, but if you put 0 in a third dimension, take the curl of that, this is what you'll see in the k component. All right, so this is what we have. Let's find out all the information that we need. So our D is the inside of the circle, which looks like we're going to go polar because it'll be a lot easier to work with. And then we need to figure out what dq dx is. So it's derivative of this with respect to x. That's just going to be y squared with a negative. dp dy is going to be the first function with respect to y, and that's going to be x squared. And then so dq dx minus dp dy is equal to minus y squared minus x squared. It looks like we might have done this before. This is x squared plus y squared with a negative, and that's going to be important and will become easy for us to figure this out because, like I said, we're probably going to go polar for this. So our double integral is going to be minus x squared plus y squared dA, with D is your circle, and so you can just easily change that to polar coordinates now. And remember that there's an extra r in polar coordinates, dr d theta, where our r goes from 0 to 2, and our theta goes all the way around to 2 pi. So this is something that we can split up. There's a -1. We'll take that out. There's an integral from 0 to 2 pi of d theta by itself. And then the other r integral is 0 to 2 r cubed dr. And so that's -1. The integral of just theta is theta. Integrate from 0 to 2 pi. It's just 2 pi minus 0. And then we have r to the 4th over 4 and put 2 in there. So 2 to the 4th is 16. So that's 4. You don't need a calculator for this, right? If it were only. If it was like this. Yeah, you would? Yeah, okay. Okay. So this is an example of Green's theorem. And imagine taking the line integral directly. So if you were to take the line integral directly, you'd have to parameterize the curve. You'd have to put those values into this, the parameterization into x and y. You have to dot that with the derivative of the curve. And then you proceed to taking the integral with respect to t. So so using the fundamental theorem of calculus is a little bit easier. And notice, the fundamental theorem of calculus didn't go from the left side to the right side. This was a boundary of something. And then we took the derivative of the function, and then we took the inside, the whole thing, not just the boundary. So that's the thing about these big theorems, is that it doesn't usually follow the fundamental theorem of calculus where we go from more integrals to less integrals. In some cases, it might be easier to go from less integrals to more integrals to be able to calculate. So we went from a single integral to a double integral. All right. Good time. Let's take a look at another problem that, There's a Stokes theorem problem. 31, 32, 33, looks like one of those. Let's pick one. Well, what? I would guess 39 would be Gauss. So if you want to do that, we could do that last. Let's do a Stokes problem. Oh, we can do Gauss now if you want. Let's do a Stokes problem. There might be another Stokes problem there. Harrison? Did you have a suggestion, Harrison? Or? No. Somebody? 32? So the thing about Stokes is looking for a flux of a curl, so that phrase should be there, flux of a curl of something. And now we're getting to where orientation would be important. So they give us a vector field. They want the flux of the curl of that vector field. And then they define the surface. S is part of the sphere, radius 5, that lies above the z is equal to 1 plane. Oh, so it's not just flat on the xy plane, so let's be careful with that. Sphere radius square root of 5, sorry, is the radius of the sphere. And S is pointing upward. So if we were to do this directly, we would be looking at taking the curl of this and then we would be looking at, well, we even have to cut this up. So we just look at the top part of this, and then we have an outward normal. And so with the outward normal, we probably want to use the dot n, define the dot n for that. And then we go through the computations, we parameterize the sphere. We have to somehow stop over here at z is equal to 1. I think that's going to make things kind of messy and more difficult. Maybe not, I don't know. But in any case, if you were to do this directly, you'll need to figure out all those little components. Now, Stokes tells us that we don't have to do this directly. Tells us that we can change our flux integral to a line integral over a curve, and that curve happens to be the boundary of S. And then now, instead of the derivative of the vector field, we're looking at the original vector field, so we don't have to do that added work of finding the curl of something. So the only thing we need to do now at this point is try to figure out what is our curve and deal with that. Or aside from dealing with the curve, is figuring out its orientation. So the orientation, if you look at this from the top, look at it from the top, you see the XY plane, and you see a circle, a radius something. We'll figure out the radius in a minute, but let's figure out the orientation first. Orientation is going to be clockwise if we are viewing it from the top. Okay? So just somehow convince yourself that that's true, because that's what we've been doing. Now, what's the radius of this thing? Radius is 2. So if you find the intersection of these two things, that's the surface of the surface has a sphere, and you have the plane z is equal to 1. you're going to get x squared plus y squared plus 1 is equal to 5, or you're going to get the circle of radius 2. Okay? So this is a line integral that we have to do. All right, so now that you got that figured out, we can parameterize it, because that's what we need to do. We need to parameterize it. So we'll start with r of t equal to, and going in a clockwise direction, this, by the way, it's a closed curve, so we use that little circle. It's going to be cosine and sine, radius 2. So 2 cosine t, 2 sine t. And this is in 3 dimensions, so we need a z, and the z just is all going to happen on the plane. Z is equal to 1, so it's going to remain constant. And then we're going to find the derivative of this, because that's what dr is going to need. So the derivative is minus 2 sine t, positive 2 cosine t, and 0. And the 0 is going to be important for us because when we take that dot product, we know that the third component is not going to play a significant role. Yeah?
Did we also solve this with the normal vector?
Well, the normal vector is for the flux. So had we been working on the flux side of it, then yes, we would do that normal vector business. Okay? That's a good question, and I see that a lot. I see that idea a lot, and I even saw it in the quizzes that I was grading this morning, the other day. So I was grading it this morning. So when you're doing a line integral, it's important that you're looking at a curve of one parameter, right? And you're going to parameterize it, take the derivative of it, and then you're going to work with that. So if you're doing a line integral, you don't need that normal vector. You don't need a parameterization with x and y or u and v, or it's a one-dimensional parameterization for the line integral. This would be for the flux integral or surface integral. Okay? So when you're working on a particular integral and you convince yourself that I'm going to use Stokes' theorem and I'm going to do the line integral and I'm not going to do the flux integral, then you have to do the line integral and you have to know what components are important for the line integral. Okay? The only way I can think about, having you guys try to remember these things is just to practice taking these things. Yeah? Probably not. But again, the flux of a curl, Stokes, right there. Flux of a curl, Stokes. And if you don't see a flux of a curl, if you see the flux of just something, then there's a good chance that that's probably going to be Gauss. Because it's not the curl, you can only do the flux of a curl with Stokes. You can write a rap about it too. All right, so now normally I put the r of t into the f function, but since I got a 0 here, let me just do this first so I can eliminate anything that needs to be eliminated, and then I'll put in the components for x, y, and z. So the next thing that goes in your line integral is this, and so our f is equal to this thing. Oh, that doesn't look nice. X squared y z, and I'm going to replace that with whatever x and y and z are in the r, times r. That's negative 2 sine t. This is a component, and so I'm taking a dot product. The next one is yz squared times 2 cosine t. And then the last one, and the whole reason why I'm not putting in the x and the y and the z into the f function is that I know this is 0 and I don't want to write that anymore. So now I'm going to drop this r, x, y, and z. So x is 2 cosine t, y is 2 sine t, and z is equal to 1. So this is going to be 2 cosine t squared. Be careful when you're squaring it. The 2 is also squared, so it's actually 4 cosine squared t. 2 sine t, and then 1. Was it? Possibly. Y is going to be equal to 2 sine t. Z is equal to 1, so you square that or not square that, doesn't matter. 2 cosine t. And then here's what you're going to end up integrating. Let's see. 2, 4, 8, 16, negative 16. I got a cosine squared t, sine squared t. And then I have a 4 sine t cosine t. The second one, the first one is not so easy. You gotta do some stuff. Unless you could factor, and can you factor and get something out of this? Anybody? Now this is where you take out your calculator. So you're going to go all the way around 2 pi negative 16 cosine squared t sine squared t plus 4 sine t cosine t. All right. Yeah. No, there's a rule for that, and you're going to have to use that. And so this is one of those trig identities that's going to need a couple of trig substitution identities to, not trig substitution, but trig identity substitutions to work it out. All right, I'm not going to do that. You guys can figure that out. So maybe a calculator would be important, huh? Well, I think if it's an integral that looks like this, I would just punch it in the calculator and your answer is going to be some decimal. Or if you have those TI-89s, then you can actually get the exact value. But all right, let's see if we can squeeze in a Gauss. 39, you said, huh? All right, so you should also remember the other form for a flux integral with the dot n business. You know that's also a flux integral. Here they give us an f function. S is an outwardly oriented surface. The boundary of the surface is this thing, and boundary of any surface cube with a unit corner and then another corner cube removed. So we know that we're not going to do Stokes for this because it's not the flux of a curl, right? The surface happens to be closed, so there's a chance that this is going to be a Gauss theorem. Well, it is going to be a Gauss theorem. It's a closed surface, and you're taking the flux of a vector field. Yeah?
Just sort of thinking about how to approach the problem, could you integrate using Dick theorem the whole 2 by 2 unit cube and then subtract the 1 by 1 by 1?
Yeah, probably. And when you say integrate that, we'll see that this actually turns out to be a nice problem because I'm looking at the vector field itself, and taking the div of that vector field will give you a constant. So that's usually a nice sign for us. If you were to do this using a flux integral directly, just imagine you got 1, 2, 3, 4, 5, 6, 7, 8, 9 surfaces to look at, and you would need to find, parameterize it and then these surfaces that look like L shapes like this, that's even trickier to try to integrate over. So that would be one side over here. So you'll have a lot of surfaces to deal with, and so there's a good chance that you don't want to do it that way. And remember, one of the problems that we had, we actually was an open surface. We closed it up, and then we're able to use Gauss, but we need to subtract that out. So that's another neat little trick to remember. So instead of doing that, we're going to go Gauss. So your flux integral is going to be a triple integral of the div. So the div happens to be the derivative of the first one with respect to x plus the derivative of the second one with respect to y plus the derivative of the third one with respect to z. So the div is just the constant. And that fits nicely with our triple integral, because whenever you have a constant, you can take that out and your integrand is just going to be 1. And we know that this is going to be the area or volume. It's going to be the volume of this solid. So the volume of the solid is it's a 2 by 2 cube. So volume of a 2 by 2 minus the volume of a 1 by 1. Right, it was taken out. So this is 8 minus 1, which is 7. Okay. We didn't even have to do any integrals here. Yeah.
So for this problem there, is it because it's a closed surface that we use Gauss's theorem?
Because it's a closed surface, yes. And because there's no curl. It's not the flux of a curl. Now, if we got an actual function in here, a non-constant function, that would have been a little bit more difficult, but you know, we can still do it this way. And like William was saying, maybe you can find the triple integral over the big solid with a big square, and then subtract out the triple integral of the smaller solid with a small square taken out. So that would work out nicely. All right. So those are our 4 major theorems that I would be asking you about. There's other theorems that I won't be asking you about, but you should, you know, in doing these theorems, you should know how to find, you know how to compute double and triple integrals, flux, line, path, and surface integrals. So it's all kind of embedded in all that stuff. All right. You gonna have fun studying this weekend? Yeah.